The gravity of the time is such that every new avenue of peace, no matter how dimly discernible, should be explored. Never before in history has so much hope for so many people been gathered together in a single organization. You will provide a great share of the wisdom, of the courage, and the faith which can bring to this world lasting peace for all nations and happiness and well-being for all men.
So we are here today with Esam Hussein, who's the Dean of Engineering and Applied Science at the University of Regina in Canada and an expert on SMRs. Esam, welcome to the show.
Thanks very much. It's Regina, not Regina.
Okay, sorry. You'd think for a Canadian university I'd get it right, but nope, always screwing it up.
No problem. Happy to be with you.
Yes. I was super excited to get you on the program after I was able to read through some of your papers. I think, you've got a very similar perspective to me when, we look at the topic of SMRs, actually asking the question, like, what is modularity? I think sometimes people don't do that. But before we get into that topic, I'd love to just learn a little bit more about you in general and what your upbringing was like, where you're from, and how you got into the sector.
That's a very interesting question. I was born in a small town in the middle of the Nile Delta in Egypt. And I went to school in Alexandria University. I really wanted to be a scientist. And my parents said, no, choose a profession. So I got into engineering. And nuclear engineering was the closest I could get into satisfying my appetite for math and physics. So it was really an engineering physics program. And at the end of my undergraduate studies, I did a master's degree in an area related to solar energy. But I was also fascinated by the CANDU technology design, in particular, the fact that it uses natural uranium. It's quite safe reactor. Make a long story short, I applied to one graduate school in the entire world to get to, and it was McMaster University in Hamilton, Ontario, because it had, I think at the time, perhaps the only nuclear engineering program in English. So I came to Canada, did my PhD with McMaster University, and then was hired by what was called then Ontario Hydro, which is called now OPG, Ontario Power Generation. And I was with a department called Nuclear Studies and Safety. And one of my first tasks was to implement some of the lessons learned from 3 Mile Island into CANDU business. As you recall, the problem with 3 Mile Island was that the operator thought the vessel really had sufficient water. The water level was rising, while in fact it was being sucked up because a valve was stuck open.
Yeah.
So one approach to deal with this is to monitor the water level in the vessel. CANDU reactor is horizontal. There is no water level. So one of my first tasks was to find a way to deal with that. And I developed a scheme to monitor the volume of the heavy water. We use heavy water in CANDU in every component in the system and see if it is increasing, decreasing, and that will give idea whether the reactor has sufficient water for cooling.
And how did you monitor the volume? Are there other easy to capture values that you can use as a proxy So for like pressure or temperature, how did you actually calculate the volume?
Exactly what you said. The computer with when CANDU, there was called dual computers, two computers, just in case one fails, the other one monitors all the instrumentation in the system. So in some cases, they're like if you have a tank, you will have a level measurements. You have pressure, you have temperature, you have flow, and if you know those, you can determine the volume of the water that is there based on physical properties. So it's essentially estimating the volume and in turn the mass from information that was already available. And that was really a condition. Use what we have.
And are in the CANDU reactors, are there sensors attached? How are the sensors distributed throughout the reactor? Are they on each fuel? I know the fuel bundles for CANDUs are much smaller, these like little, canister sized things. Did they each have a sensor, or do you have to measure it in aggregate across a longer column? How do you take the measurements?
Yeah, there are some what we call the CANDU reactor will have typically 300, 400 channels. And there are some of them that are fully instrumented. They're called the instrumented fuel channels. And they are really representative of the core. So you have that information available, the inlet flow, the inlet pressure, the inlet temperature, and on the other side of the channel. The idea was really what you're looking at is measuring change rather than measuring absolute quantities. So if the water is swelling, the volume will go up. If it is going down, you lose it. And I should tell you something interesting I remember from those days. Well, if you look at any instrument, particularly pressure measurements are very noisy. So I added artificial noise to the simulated data I was getting in a way. And I showed the results to my supervisor and he said, how did you create that accent? That was all simulation, right? Simulated accent. I said, it wasn't an accent, it was just noise. Yeah. So noise can give you, in a way, it can mislead you.
Yeah.
And so we took care of this. And after about close to 4 years, there was an opportunity to move to the academia. So I applied for a position at the University of New Brunswick in Eastern Canada, which was starting a nuclear option, as we call it, in mechanical engineering and chemical engineering. Just happened, my boss at Ontario Hydro occupied the senior chair there, industrial chair, and I joined him. And this is where really a turning point in my career. I'm showing my age here, I guess. One of my colleagues passed away in the infamous Air India bombing, where a plane was brought down.
Mm.
And he left behind a young family. And I decided that from that point on, I'm going to devote my career in a way, or my research program, to detecting what I called contraband or threat materials. So I got into the detection of explosives and luggage, eventually landmines, and narcotics in general. And my research started looking into the non-power applications of nuclear radiation, a bit of medical imaging, non-destructive testing, industrial non-destructive testing, and so on. It's a very satisfying career for a number of reasons. It was open opportunities. I had a sense of mission. There was funding. And it's my really dream was when you walk into a hospital, you find a nuclear medicine department and the radiology department. Why don't we have the same thing in industry? It's the same really diagnosis techniques.
Yeah,
right?
yeah, amazing. Yeah, it's true.
Yeah. Anyway, I spent almost my entire career in that field. And almost about, I guess 7-8 years ago, I got recruited for a dean position here in Saskatchewan at the University of Regina. And as you know, Saskatchewan is a uranium producing province. But the uranium is exported with really very little added value. And the province as a whole was talking about SMRs, small modular reactors. They're really looking at small because the grid is about 1,400 megawatt. And if you get one of the usual conventional reactors, which is about 1,000 or so, 900, and it goes down, you lost most of the power. So their ideal power station should be in the range of 300, 400, 500 megawatt. There was talk about it. There was no commitment, but there was talk about it. And it whet my appetite as a nuclear engineer. And I looked at it this way. In a province that has no nuclear power, the first step will be to find a site where to put the reactor. How do you select a site? In Ontario, for example, this has been done, and there are sites that already has nuclear reactors. New Brunswick has sites as well. The site selection is very interesting because it's not only a nuclear engineering problem, it's actually very little nuclear engineering. It is all the other fields. And I thought that would be a great idea to get my colleagues in other disciplines to be aware of how thorough in the nuclear business we do things. So I put a team from the two universities, University of Regina and University of Saskatchewan, that varied from, for example, a lawyer who looked at duty to consult with indigenous people and how would that affect the site selection, to geography, geology, water management, transportation. If you're going to transport nuclear material, do we have the routes? What are the best routes?
And did you pursue this analysis with some sort of technology agnostic framework? Because it seems to me that there is there's a coupling of the unique characteristics of some reactors versus others in terms of their impact on the environment, and certainly even just on like the balance of plant side in terms of water consumption and what technologies you're using. How is that factored into this site analysis?
This is a very good question. If you look at it from a risk analysis point of view, we look at what we call the source time. And that is the amount of radioactivity that can be released to the environment in case of an accident. Well, the radioactivity, every reactor has nuclear fuel. And in case of an accident, some of that radioactivity will be released. From a point of view of site selection, you want to choose a site in which really can obviously evacuate people as quickly as you need, minimize the contact between the radioactive material and the environment. So water streams, wind, and so on. So to answer your question, yes, we looked at it as selection of a nuclear facility. Some technologies, for example, if you have a reactor with a double containment, double containment means if radioactivity leaks from the first containment, there is a second containment. Or if you have a small modular reactor buried underground, there are protections. But nevertheless, we assume that some level of radioactivity will be released, and we want to choose a site that minimizes that.
Can you explain the double containment principle a little bit more? Are there certain reactors that is more common on, or is it just a design choice, irrespective of the reactor, that you'd factor into your containment design criteria?
The double containment business comes from the oil industry shipping oil in vessels, right? Sea vessels. And that's essentially the idea, is to, if oil leaks from a vessel, it will not leak into the ocean or the sea. Not all designs have that, but there is a particular design, the Indian small modular reactor is designed that way, to have a double containment. If you put the reactor underground, in a way, you have the reactor containment and the ground as a containment. In essence, in a CANDU system, you really have double containment indirectly, because, as you said, the CANDU system is a pressure tube. The pressure tube means that the vessel is designed to withstand pressure, and that's a containment, and you get the outside containment. In a pressurized water reactor, you have the vessel, which is self-containment, and you have the containment structure itself. Chernobyl's problem was that it didn't have the outside containment. So in essence, the concept of double containment is already existing. It's just been articulated as an extra layer of protection. So you will have, in the Indian design, for example, you have the pressure tube, which is also the Indian design, is pressure tube based. You have the regular containment, and you have an extra containment. And that, as you can tell, created a dialogue among people. The questions you just asked. So that project just finished, and in a way, just by luck, it was timed so that it finished at about the time the province formally committed itself into looking into small modular reactors. And an idea, of course, is to have people who can assist the province, and so I've graduated, I think it was about 25 graduate students that came out of that project. It involved 14 faculty members as co-investigators. So there are people there with expertise. We even looked at grid considerations, right? As I mentioned, the grid can take about 300, 500 megawatts. So what's the effect of having an SMR in that grid? Can the SMR output follow the demand? If the demand goes up, can you increase the power? It goes down, can you use the power for something else? And also looked at cybersecurity, because some of those reactors obviously will be connected to the grid, and they may be vulnerable. So choosing a site where this grid cybersecurity is assured is very important. Many factors. And it was a fascinating project. Then I think the reason you're talking to me is because you saw my critical review. I took a 6-month research leave from my first term as a dean, and I decided to dig back into the history of small reactors. Small isn't new.
Yeah.
The reactor concept isn't new.
Yeah.
So what obviously is new is two things: the modular and the generation 4 designs. And that is the essentially inherently safe, passively cooled and controlled system in a way. And I spent 6 months going back into the new designs. There is 100 plus new designs and old designs. And to my delight and surprise, in a way, I realized that all those designs have been tried in the past.
Yeah.
That's good because it's reassuring.
Yeah.
And you can obviously add, and some designs do this, new features to add protection and add safety, and make use of the operating experience we had for decades. The modular is the thing that I found difficult in the literature really to pinpoint and say, what does it really mean? And I can talk about this if you like. But again, just like the double containment, it goes back to the shipbuilding industry, where the idea is that shipbuilding can, like any other mega project, is usually behind schedule and over budget. So the shipbuilding industry looks at building a ship from modules that are manufactured off-site, bring them and assemble them to save time, construction time, and avoid cost overruns. So that's one definition of modularity. The other definition of modularity is to build a power station from small units. If you need 1,200 megawatts, you don't have the money, start with 300. And when the money comes in, you add the next unit, and so on. So a commitment in terms of capital cost is much less. And in a way, most nuclear power plants are built from 4 units, really. Sometimes they're built at about the same time, but usually they are staged in. And the difference, of course, is rather than building 1,000 times 4, you're building 300 times 4. In my view, that is really an old definition of modularity. The interesting thing in modularity is what I said earlier, being able to build components off-site, test them, bring them and assemble them on-site, and to save the construction time, the construction cost. I may not have access to industrial information, but at least in the open literature, the information that's available, in my view, is quite thin.
So and I'd like to hear your reflection on this, because one thing that I've seen that's, I've seen a big difference between modularity as it exists in other industries and how it's shown to be economically successful, and then modularity as we've seen from some of the nuclear startups that claim to be modular, but in my opinion, somewhat miss the point of the modularity. So in one of the cases that you gave, where you say you're adding additional modules over time because you can't afford, or maybe to kind of spread out some of your cost. It seems that only works if what you're adding in each increment is a significant portion over the overall expense. But if you build this facility, with the anticipation of 12 reactor modules, and you're paying for 85% of your total facility cost up front and only saving 15% on the additional module units, I feel like the economics don't work to your advantage. That it makes more sense with the previous instantiation of building multiple totally independent units on site, where you really do get to, if you have, let's say 4 units, you really are only taking 25% of the cost after your first unit is built. Can you reflect upon that?
This is a very good point. It's like every other mega industrial project. And I don't know why, but most mega projects end up being over budget and behind schedule. Because mostly we don't really know the unknowns we're going to face. So we'll need thorough economic analysis to decide what's best for a particular jurisdiction. Some jurisdictions may have the need and the money, and they can go the way you mentioned. Some others may not have the money now, and in a way, even it may appear as initially a bit costly to go that way, because as you said, once you build an infrastructure, you really have to build it for more than one unit. But if you don't have the money now, and borrowing it can be a bit a burden, then that's a choice. It's a political and government decision in which way it goes. Whether you do it all at once, you do it in stages, I think the cost or the benefit we're going to get from the reduction in greenhouse gases is going to play a big part, because there is now cost to building a fossil-fired station. Aside from the capital cost, there is the environmental cost. And carbon pricing now in most jurisdictions is becoming a big issue. So these factors have to be really taken into consideration. If I were a decision maker, I would simply look at it as a small reactor with modularity as an add-on that may have some benefit. If I were a vendor, I want to demonstrate that I can build a plant on time and on cost.
Yeah. The other aspect of modularity that I've seen interpreted one way, but looking out to other industries I've seen work successfully, a different way, is this idea of breaking things into nice small modules, like the ship industry that can get snapped together on site, versus what I've seen sometime in the nuclear industry as the interpretation of modularity is they put as much as they can into a single module, and make the largest monstrosity of a complex piece of technology, kind of like an airplane, and then ship that thing to the site. Do you also see that dissociation between what the nuclear industry does and what other industries do in terms of that quality of modularity?
Well, both of them, in a way, have pros and cons. When you build small units and assemble them together, the communication between the units and the fitting, not only in terms of structure, but the fitting in terms of instrumentations, in terms of fluid flow, in terms of controls and all that stuff, becomes complicated. And some people think that modularity, in a way, hinders innovation because it limits your ability. If you go the other way, a unit altogether, you obviously, hopefully, reducing the construction time and the cost. What fascinated me going back to CANDU is that's quite simple. In essence, each pressure tube is its own standalone reactor, if you like. Cannot be critical, but if you have a problem with a pressure tube, you can deal with it. You can plug it, you can replace it. And in a way, you can think of the CANDU design as a modular design. 380 channels, each one of them is a module. You can manufacture those offsite, bring them, assemble them, put them together, build a vessel, right? And add the feeders from both sides. And so we will see. we will see. And that is
I think that's one of the very interesting things about the CANDU. And one of the things that I like in terms of modularity is how it's broken into so many of the same piece. You know, you just stack them together. I like that. It seems to make more sense to me.
Yeah, and that's one of the things that really I found interesting. Just up to recently, there was no CANDU SMR. CANDU Energy came up recently with a design. In a way, there has been a 300 megawatt electric CANDU design. There is also experience with natural uranium using organic cooling. It was a reactor that ran in Pinawa, Manitoba, what used to be called White Shell Laboratories. The advantage of using natural uranium is, of course, you don't depend on another country to provide you with an enriched fuel.
Right.
The disadvantage is that because if it's not enriched, you have a lot of uranium-238, which can, in the reactor, some of it is converted to plutonium. So it becomes a nuclear safeguarding issue. But I think that is doable. When I talk to colleagues and ask why don't we have, simply we don't take a CANDU reactor, just reduce the number of channels and you get the power you want.
Yeah.
And I even dreamed of a one-channel reactor, right? If you want to go that far in terms of small, it's really, they think it is the capital cost.
Yeah, it's a fair point. What you're saying is the overall capital cost of the system, there's some fixed costs that you have no matter what. And so irrespective of your reactor, if you go too small in terms of your power production and revenue production, you might never pay back whatever those fixed costs are just simply because it's a nuclear project or because simply it's any power plant infrastructure. And that sets a lower limit on the size you can go. And then it's almost, there's some function that shows the profitability as you go greater than that, up to a certain point. Is that the point that you're making?
I think that applies to any mega project. You're aware of the hydro project in British Columbia and in Newfoundland and Labrador. They face the same problem. CANDU is a bigger reactor. It's a big, physically big, because it uses natural uranium. And with natural uranium, you don't have enough fissionable uranium-235. So it tries to save every neutron that's produced by avoiding absorption. And this is done by using heavy water. On the other hand, you want to slow down the fast neutrons that comes out of fission so that they can cause fission.
Yeah.
So heavy water is not a very effective way of slowing down neutrons compared to light water. Light water has hydrogen, heavy water has deuterium. So you need quite a bit of heavy water to do that.
You mentioned organic coolants. Is there a good organic coolant that has the right cross-section of absorption to cross-section of reflection parameters that you'd like?
Yeah, I don't remember the name of exactly the coolant that was used in White Shell WL1, as you call it, the White Shell reactor, which ran as a neutron source for a number of years. Yeah, you achieved criticality. You can do that without heavy water. There are organic coolants that can do that. There were problems with stability and so on. My understanding that the reactor ran for a long time. They're able to overcome that. Using natural uranium is advantageous for some countries. The other aspect is that those reactors can also burn fuel produced by burn plutonium in essence.
Yeah.
So, and that has been studied and can do bring spent fuel or weapon grade plutonium from some other countries and burn. I am biased towards CANDU for a number of reasons, I guess. Being in Canada is one big part of it. The industry has a superb record in terms of safety. And in essence, because if there is a water leak, it's going to be in one channel and you can control it. And it will leak into the moderator, which is a huge pool of heavy water. A number of reasons. We have many years of experience. So the challenge that faces the nuclear industry has been always, in my view, public acceptability, social licensing, if you like, and to some extent, technical licensing as well. And I think, and I could be wrong, the cost of building the first of a kind SMRs physically may be comparable to the cost of licensing it.
Crazy.
The reason I'm saying,
but it was just, this drives me crazy because it's like, imagine if you were to say the same thing for like a skyscraper. To me, a skyscraper has a way higher element of risk if it's designed incorrectly, because there's, you know, thousands of people inside of it. It can be hit by an airplane, just like, you know, we have to protect against in the nuclear industry. And yet the costs to license a skyscraper never come close, like maybe 1% or 0.1% of the cost to build the skyscraper. And yet you still have to do the right, like the same things. You have to make sure the steel is good, the concrete is good and is poured well, that, you know, that they're certified professional engineers that looked over your structural calculations, that it's seismic. You know, it's like we have to do all these things for a skyscraper. There's way more lives at risk in a skyscraper, and yet we managed to do it, 100 times more cost effectively than a nuclear plant.
Well, I was reading recently on the 10th anniversary of Fukushima, the number of people who died in the evacuation or injured is much higher than the number of people who would have died if they stayed and exposed to radiation, because the amount of radiation level was low. But here is the difference. When a building collapses, yes, unfortunately, people die, and you will get more people dying than you will get, and you'd have because of radiation in any of the big 3 Mile Island, Chernobyl, or Fukushima. But it's done with. When a nuclear accident happens, you live with it for a long time. And so the regulators, rightly so, don't want this to happen.
Yeah.
And
yeah, no, listen, I agree. We don't want accidents to happen. My only critique was that it can't be done more cost effectively, given that at the end of the day, it's engineering. And I mean, I think part of the problem is like our approach to licensing. Our approach to licensing is, well, at least in some countries, is so prescriptive, rather than just kind of achieving safety goals and allowing the vendor to describe how they achieve those safety goals. And even in the countries that say that they're not prescriptive and that they say in the law, yes, you, the vendor, bring your idea to us and tell us how you are going to achieve safety goals. Culturally, they're still prescriptive. Culturally, they still want you to do the same checklist as a country that has in law that you have to meet these criteria, even if they say they won't.
That's why I am inclined to support the devil we know. In essence, CANDU designs are well tried. PWRs, pressurized water reactors, being used. We had them even submarine reactors, boiling water reactors. It's much more easier to license those, scale them down, try to bring the cost of construction down, capital cost down. You will have a much easier time with the regulator because of the tremendous amount of operating experience we have. If you go back to the history, why all the other technologies, which really started in the 50s and 60s, Why aren't they dominant now?
Yeah.
They found reasons to terminate the programs. Some people say it was political. Some people say it was lobbying. But the fact of the matter that the three technologies I just mentioned survived and endured.
Yes. Yes.
Right?
Yes.
Yeah. So if we want a quick solution and build reactors so we can offset the carbon emissions, start with what we have.
I couldn't agree more. I literally couldn't agree more. And yes, for the reason that you mentioned, listen, there's like, these were the ones that survived and prospered, I think, and I'll just speak to that for a second, then I'll give another reason around supply chain. But I think what people tend to overlook, especially if they've never started a company before, or they've never been responsible for developing a totally new technology before, is that the reality is different than what's on paper. And it's only until you actually try to build something that you understand like the really fine-tuned reasons that might affect this odd operational characteristic or this odd maintenance characteristic or this odd, we can't find enough welders for this really weird alloy that we need. That it's like, but we do have this, the historic, well, at least we have this empirical evidence of, hey, we tried these 50 or 60 different types. For one reason or another, they were discontinued, and these three, moved forward. And I think that's like that gets discredited too much about like how that history, how important that history is in terms of giving us a clue to the unknown unknowns that might affect cost and engineering challenges.
One big factor that's causing this indirectly, I think, is that the nuclear industry has been stagnating for a few decades now. Since 3 Mile Island, the expansion has been very limited, which meant also the experts and the expertise in design and construction retired, faded away, or died. And I'm very likely among the youngest, and my time on Earth is limited. We lost tremendous amount of knowledge and expertise over the past 3 decades in terms of design and construction of nuclear plants, design in particular. And with due respect, yes, great new ideas are great, but why don't we build on what we know best?
Yeah,
and improve on it gradually, sensibly, and take the time to let other industries evolve. Traditionally, and I don't know if that's good or bad, but traditionally, the nuclear industry is and was dominated by big companies, by big utilities. They have the ability to invest human resources and technology and have long-term goals. And I hope that stays that way.
Yeah. Supply chain in general, I mean, your research, have you come across, that's the other thing that always comes to mind when kind of focusing on like, how to like get going again. One of the other things that I like about, sticking with the technologies that you've identified as the ones that have kind of made it through is that there's still, even though it's a dying supply chain, there is still some supply chain, right? You can get, you can buy PWR fuel bundles, you can buy CANDU fuel bundles tomorrow. You don't have to spin up a brand new factory to supply your fuel. And then not just that, but other components and systems as well that are identified and common amongst PWRs, BWRs, heavy water reactors. You can pretty much buy one of anything that goes into that reactor today if you needed to. Does that play a role at all in terms of how you see where to direct your development efforts?
Yeah, and I can add to that. you very likely will buy better components as well, because there has been development in materials and there have been learning processes that went through. We know now where if the material is weak in something, we do something about it. The pressure tube is a good example in the CANDU business. And so you not only have a supply chain, but you also getting a better product. Even if the supply chain is weak, as you said, there is a nucleus you can build on.
Yeah,
you can always bring it back very, very quickly. This, in addition to the licensing, in addition to the operating experience that we have for decades, will add up to a product that is very likely reliable. You may have still some challenges in cost overruns and delay in construction and so on. It's just inevitable with any big project, because you can't control the outside forces.
Yeah,
you can't control labor disputes, currency fluctuations, and so on. But the new technology will face the same thing.
Yeah, that's right. What about switching gears for a second? Have you looked into the Slowpoke reactor? That's a version of the CANDU, or is it heavy water? I know that was another smaller reactor that was supposed to come out of the Canadian industry.
Yeah, this is really a subcritical assembly to produce neutrons.
Okay, that's all. Okay, that's a Slowpoke.
Yeah.
Okay.
Yeah. It's a small, it's a small reactor, and of course it uses highly enriched uranium, downgraded a bit with the new regulations, but it's not a power plant.
I see. No,
yeah. The closest. Sorry.
Please continue. No.
I was just going to say the closest to small middle reactors are submarine reactors.
Right. Internationally, who do you meet with on this topic, across the world to share learning? I mean, imagine the Canadian nuclear industry is tied to Romania and Argentina and maybe India, maybe a few of the heavy water countries. Are those the ones that you're closely tied to as well, or do you participate in other international forums as well?
Well, I have to confess, I am an independent academic researcher. So, and being out of the nuclear power business, as I mentioned earlier, most of my career was in non-power applications. I haven't really established the personal contacts. And I think this has been advantageous in being able to provide a neutral point of view, not influenced by, you are all human, right? You interact, you get biased. I was surprised and amazed of how much information is available in the open literature from the 1950s, 60s, and 70s. And if you saw my paper, it's about 200 references. And the information is rich.
Yeah, it's amazing.
And we can go back and build on those and learn from them. And hopefully that will ease and facilitate the licensing process a bit.
Yep. Yeah, one of the other historical points that I think kind of changes maybe a little bit of the cost calculus as to whether to go big or small is that back in the day, because we had less like in the 50s and 60s, we didn't have as many computerized systems to run power plants in general. And not just the whole power plant, but let's say a chemistry system or chemistry skid or something. So you needed these 500-600 people to run a power plant, and it didn't matter if it was coal or nuclear. You just needed hundreds of people because there was no automation. And so of course it made sense then to go bigger and bigger and bigger. But now you can see, while nuclear industry still has 500, 600, 700, 800 sometimes people per power plant, mostly by regulation, the coal industry now has 20 people per power plant. And that changes the ratio of capex and opex. And And I'm wondering if there's ever been, if you come across any analyses that say, one of the reasons that we just didn't go smaller with nuclear was because we assumed this high operational cost for just the amount of people that you needed to run a power plant. But if the nuclear industry would adopt the same personnel profile that a coal plant had and only now needed 20 people instead of 800 people per facility, that might allow us to go smaller and still be cost effective. Did you come across any analysis like that in the literature that you read?
No, actually, my understanding is that most of the people who work on a nuclear plant are not really in the nuclear area. It's a power plant. Once you produce the heat, it's a conventional power plant. The number of nuclear engineers you will need, mostly for fuel management and for criticality analysis, is a very reasonably a small numbers. CANDU reactors have been always computer controlled. And there was a debate after 3 Mile Island 2 accident, what's better, operator intervention or computer control. So I'm gonna put it that way. My understanding is in nuclear power business, the big cost is the capital cost. The operating cost, even if you have more people, is lower than conventional power plants because the fuel cost is really low. Once you build a plant, the operating cost. So that may not be a factor. What will be good, and many have done that already in the nuclear industry, is 2 things. One is using the available data to provide better monitoring of the current status of a system and perhaps extrapolate and predict the behavior of the system. That computer power can do that. The other thing, which again was a result of the unfortunate 3 accidents we had, is better communication between the operators. Where the industry really should be and is getting close to being cooperative rather than competitive. We learn from each other because it's an industry where one mistake in one place affects the entire industry. So, and it's easy now, you're communicating with me and miles away. It's much easier to do that.
Yeah.
Talking to each other, opening up, being honest about what's right and what's wrong and how we can improve, because they're all in the same boat.
Yeah.
They're all in the same boat.
And then I wanted to pick up on one thing you mentioned before, just because I'm less familiar with the CANDU systems. Can you elaborate on the computerized control and how that's set up? Does that mean that operators don't make decisions unless there's like a true emergency and everything is just monitored and adjusted by computer for between, just, I guess with a CANDU on an ongoing basis, right? Just because the refueling happens continuously while the reactor's still online. Does that mean that really there's no one in a control room that's turning a dial that says, let's turn down power or this or that or anything like that?
Well, they can turn down power up and down, but in terms of a reaction, if there is a significant event, the computer will kick in. So they'll sit back the reactor in terms of power if things are not going in the right direction. They have a dual control computers, so that 2 computers are running at the same time, just in case something goes wrong with one computer, the other is available. All the instrumentations are typically triplicated. So you have 3 sensors for the same thing, and the computer system will kick if there is a 2 out of 3 vote.
And on that note, just a quick question on that. Is it continuously doing a majority voting, or is it relying on a specific sensor or an averaging until they see that there's a big problem with one of the potential sensors, and then it switches to majority voting?
I can't answer that directly, but any control system will be based on what we call trip points or set points. So if the pressure reaches a particular certain level, then the control system will kick in. It may have to trip the reactor, meaning shutting it down completely. I'm not an expert in controls, but I think common sense says you base your system on the most dominant factors. Temperature and pressure and flow are obviously very important parameters. There is also flux mapping, and that is neutron sensors that give you the flux level in the reactor at different places, and you map. The computer will map those and will make a decisions on those. The idea is to have as much as possible flat distribution of neutrons and power in the system for best burn up and to avoid oscillations within the system. And the control system will try to adjust that as needed as well by control rods going up and down. So operator intervention, as far as I know, is minimized, and they get quite a bit of training on simulators. Simulators is a big business, I think, in every industry, every nuclear industry, as much as the aerospace industry. It's proved to work well. Early on, there was a debate on digital versus analog control. I think these days are over now. But the fact of the matter is that most of the systems were designed in the 60s and 70s.
Yeah.
So that's an area of improvement, obviously, in terms of digital versus analog.
Yeah, absolutely. Another point that you made earlier that I wanted to come back to was the ability of the CANDU reactors to consume the waste of other reactors. Has that ever been tried where it's literally as explicit as, let's take an old PWR fuel bundle, which we have a lot of sitting around our country at least, pop open the top, pour the, in a controlled environment, of course, pour the pellets into a CANDU assembly and just literally shove it in and let it go? Has that ever been tried?
I'm not sure, but if I remember correctly, there were attempts to look at burning weapon-grade plutonium in CANDU reactors. Whether this has been done or not, I'm not sure, but I know that there were studies as part of the treaties that were signed between the former Soviet Union and the USA in that direction. When you really think of a CANDU fuel, you have a very small amount of uranium-235, 0.7% or so. The 99.3 or so, the rest is uranium-238. So what happens is that uranium-238 absorbs neutrons and is converted to plutonium-239. So the reactor runs on that plutonium as well, because it's produced within the reactor.
Yeah.
And you continue doing that until the amount of neutron-absorbing fission products overcomes the gain you get from production of plutonium. So you can say that the CANDU is a plutonium-burning reactor.
Yeah.
The difficulty comes when you have a spent fuel, you have a number of neutron-absorbing fission products.
Yeah.
And you have either to wait until they decay, or you have to extract them from the system, process the fuel, and bring it back. Some of the new designs, SMR's designs, are burners. They're designed to burn that way. The other thing which is fascinating, I think that applies to most reactors in a way. You can surround the reactor with thorium and produce uranium-233. So you put a blanket around the reactor, and you take that uranium-233 and use it as a fuel as well.
Yeah, but I think the only problem with that are the proliferation concerns, because you have to let it decay through the protactinium 80-day decay half-life. So you've got like these buckets of uranium-233, which is all weapons grade, just like sitting around somewhere.
Yeah, and this is another factor with the nuclear industry, in a way. Depends on the user.
So actually, can I ask on that real quick? Is given that the thorium-232 has some similarities in its ability to fission as the uranium-238 does, since they're both even numbers, can you just put thorium straight into a CANDU and not have to then like remove it outside for its decay chain to follow and just hit it directly, or do you still need to separate it for a period of time?
Well, thorium is a neutron absorber. So you convert it into uranium-233, which is a fissionable material. So if you put it inside the core, you will have to compensate for the neutron absorption some other way.
I see, right. Okay.
But if you put it as a blanket outside, the neutrons are escaping from the system anyway. And so rather than escaping and absorbing them in the structure, absorb them in thorium and convert the thorium-232 to uranium-233. So it's really the uranium-233 is a fissionable material.
Yeah. But you could also do that with just depleted uranium. We have plenty of depleted uranium sitting around, and you could also create a blanket out of that, right?
Yeah, I agree. This is another aspect of using enriched uranium, is the generation of depleted uranium and what you're going to do with it, right?
Yeah.
It's a good shielding material, and it can be used for some industrial purposes. But as you said, you can also breed that to plutonium.
Yeah. Great. Okay, we've covered a lot of topics today, and this has been very interesting. I'm wondering, just before we wrap up, if there are any other topics that you wanted to share with the audience, or that you or just kind of insights that you want to share.
Yeah, the only observation I have, and I could be wrong, but it came as a delightful surprise to me, is that young people like yourself, and young women in particular, are getting interested in nuclear power because they see it as a way for the future. And it is that generation, your generation, and the generations that will come, that will benefit from the nuclear industry. And if we take a long-term point of view, I was born in Egypt. So 500 years in Egyptian history is a short period. The pyramids have been there for thousands of years. The country has been occupied and invaded and so on. Keeping nuclear spent fuel for 500 years is not unreasonable. And think of those materials when they decay and cool down, all the precious metals you're going to get out of that, and all the new nuclear fuel you're going to get out of that.
Yeah.
So in a way, I'm saying the youth, on one hand, are the hope for the future, and the old as well. Taking a long-term point of view, we are facing a climate change crisis.
Yeah.
we need all the help we can get. And the other point I would make is that nuclear power will aid in introducing more solar and wind energy because you have a reliable backup. That's always there when the wind is not blowing, when the sun is not shining. You can use nuclear power. And when they produce the electricity, you can use the nuclear power for some other purposes, water desalination or process heat, or even hydrogen production. And if you use it for hydrogen production, you are using it in transportation, you are reducing the greenhouse gas emissions and so on. So nuclear power can play a big part. I'm still of the belief that yes, the licensing process is more rigid than any other industry, but in the long term, it protects all of us. I think it's a short-term pain for a long-term gain, and I think that has been proven. So that's just some of the thoughts I have.
Yeah, thank you. Well, Esam Hussein, thank you so much for taking the time today. This has really been a pleasure talking to you, learning from your expertise, and hope to talk more soon.
Thanks for giving me the opportunity. It was a pleasure.
And initiate at least a new approach to the many difficult problems that must be solved in both private and public conversation if the world is to shake off the inertia imposed by fear and is to make positive progress toward peace.